So I receive a lot of emails on about careers in analog and RF design, and especially what are the areas to work in, and what are the hot areas to work for. So I'll just roughly give an idea about that in this lecture, and also probably talk about MS or no MS. Is MS a good option? I'll briefly talk about that, and PhDs and or working in industry. I'll try to give a comparison for all of that. So analog design, very broadly, we have three. You can classify it into three areas. One is the baseband or lower frequencies. Other one is RF and microwave, and the third one is terahertz. So usually, what happens is that the way in which semiconductors itself, the field itself is like 60 years old, right? 1960 MOSFET was invented. We had circuit design even before that. But after that, when integrated circuit took over from 1970s, when computers became popular, we saw computer revolution. Then we saw cellular revolution. Before that, we saw telephone industry. Okay, so each industry, each product brought with it a lot of new design challenges. So then, once computers became popular, there was internet. Okay, so internet brought about huge changes in circuit design. And after that, now we are in the age of wireless connectivity. So we have cell phones and devices. Almost every device can wirelessly connect with each other. So we are in the age of wireless connectivity right now, a very high speed. So as we move to these different technologies, broadly we can see analog design research has been, I've classified it based on the frequency of operation. So we have baseband or low frequency circuits. Then we have the RF and microwave circuits. So typically these operate in the frequencies of 6 gigahertz or lower, or now 5G, they go in the range of 20 to 28 gigahertz. And there are different bands, but say less than 40 gigahertz. So those are the frequencies of interest we are talking about. And I'm calling it as RF and microwave frequencies. After that, we have terahertz frequencies, which is in the order of hundreds of gigahertz. Okay, so these are the three ranges of frequencies where analog RF circuit designers work in. The trend has been, in fact, pioneered by American universities, and now it's a trend that's catching up even in Indian and Chinese universities as well. Is that universities usually do research work that is 10, 20 years ahead of industry. That's the general trend. Okay. Most of the blocks that we do today, whether it's, so when we talk about, and then one other thing which I wanted to mention is, of course, broadly, I can put it as baseband, RF, and terahertz. And then there is this mixed signal, which overlaps between baseband and RF. So we have ADCs and PLLs, especially ADCs, which operate at very low frequencies to even gigahertz of frequencies now. So that's why I've just put it. It's a very nebulous. I can't put it in a single frequency range. The frequency is quite spread over from baseband to RF and even millimeter wave for mixed signal systems. So engineers work, analog RF engineers work in different areas. So there are some engineers who work on different blocks. They move from low frequency circuits to RF circuits at some point in their career. And if they're bored, they move to mixed signal circuits and so on. And there are some engineers who decide to work on one specific area, one specific frequency range throughout their career, and they become domain experts. Okay, so I'm talking about engineers working in industry. They become domain experts in one specific area. Now, where we are right now, see, every time, it's like I said, it's been 60 years. The field itself has evolved significantly. So university research has also contributed significantly to the current day industry standards. So if you look at it, baseband generally concerns with circuits which operate at very low frequencies. So like low dropout regulators, some filters, op-amp based filters. So these circuits, the negative feedback based circuits, they operate at very lower frequencies, in the order of kilohertz to megahertz. That's what I'm calling it, as few tens of megahertz or even 100 megahertz. I'm just calling them as low frequency circuits. Then there is power electronics, which is nothing but circuits which go into the power. EV is becoming very common now, electric vehicles. Circuits that go into all these electronic devices, electrical power devices. So that's another field which is being emerging for the past 2 decades. So that is also another interesting field. And both these fields, they deal with lower frequencies. Now in power electronics, what you need to know, again, you need to know electromagnetics. So electromagnetics is something which is common for at least 3 different fields. Power electronics, you should know electromagnetics. RF design, you should know some electromagnetics. And even in terahertz, you need to know basics of electromagnetics. Now, where we are right now is that, see, most of these, for example, baseband, RF, mixed signal, most of these circuits, universities have been working for the past 40 years. So there is a lot of research in LDOs, or low dropout regulators. A lot of research has gone into ADCs and PLLs. A lot of research has gone into LDO, power electronics as well. So right now, universities don't focus so much. I'm talking about American universities. Majority of the top schools, they are focusing in the terahertz range. Because right now, even the faculties that they are hiring, the research, the focus is in the terahertz range. Because these two areas are now the main focus of industries. Now, industries are pushing these blocks to the limits. We are building PLLs with extremely low noise numbers, which we wouldn't even think of 10 years ago. But all this research, which was required to push the PLL noise to lower and lower numbers, was done 10 years before in universities itself. Okay. So today, even in radio frequency circuits, RF and microwave circuits. So we have this, especially in 5G, which is 28 gigahertz and so on, we have this circuits called phased array antennas, where those ideas that you can transmit at high frequencies, mobile communication is possible at high frequencies. This was proven in 1990s. Okay. At that time, there were only few groups which were working on this. And in 2000s, almost 15 years ago, many the professors were hired in this field, which was in the range of few. RF was a in thing, and professors were hired in the field in America. And a lot of work went into demonstrating circuits that would work in the RF and microwave, which is in the 6 gigahertz to 28 gigahertz range. Now it has become industry standard. Okay, so that's the goal of university and industry. University demonstrates the feasibility. Sometimes some profs take those feasible ideas and start companies. Sometimes they just demonstrate and move on, and industry takes over, and the startup ecosystem works on it, and the industry eventually catches on. So that's the way. There are two groups of professors, academicians in America, that they work. Now we are catching up in India. We have been able to publish papers at least in mixed signal and in RF design. Terahertz is still not very popular in India, but it's an area, the expertise is very few people are experts in those areas. The problem, I'll come to that, is that, let's say you work in a terahertz, you've spent 3-4 years in doing a PhD work in terahertz frequencies. When you come back, the opportunities in industry is very few, because most industries are working in this range, baseband and RF and microwave and mixed signal. This is where industry is working on. Okay, they are trying to perfect it. We are pushing ADCs, we are pushing PLLs to the limits, we are pushing RF and microwave circuits. So RF and microwave circuits here refers to local oscillators, mixers, power amplifiers, LNAs, switches, RF switches. So all these circuits are referred to as RF and microwave. These circuits are being pushed to the fundamental limits. What is the best you can get out of a device, of a circuit? And that is being now pushed to industry. So previously it was in the realm of the universities. So universities demonstrated the feasibility, and some of them have come to start companies in those areas, and others have moved on to different areas. Some of them have some research universities which were doing active research in 2000s, now they have slowed down, which were doing in mixed signal. So typically you can expect a group to be doing, usually groups are run by a single professor. So when the professor move out, then a new person takes over or they start a new group itself. So a professor's active career will be 30, 40 years max. Okay. So in 30, 40 years, you can see the changes they can bring. So that's generally the way the education system works. They show some feasibility and industry takes over after some time. Also, sometimes industry itself pushes for research. TI had done that in 2000s. For PLLs, they did that. They pushed the digital PLL architectures, which was not done in universities. It was done in industry. So only after 15, 16 years after the industry, then the work slowly reached to public domain, where people could read it and publish it and all that. Okay. So that's the general career approach. So now the thing is that you can do, if let's say you want to do research in these areas, you want to go to universities, and if you have plans for PhD, these areas are good to do PhDs. But keep in mind, you can do very high quality work in the right analog teams in the country or in US itself. Okay. And because PhD is 4 to 5 years of time investment, you have to invest 4 to 5 years of your time. And in those 4 to 5 years, you will lose a lot of money. If you're in industry for those 4 to 5 years, so because if you're going for a PhD, it means that you already have your master's degree. So after your master's, if you're going, you are better off in an industry doing 4 to 5 years of research work. I mean, solid work. So you just have to find the right team. If you don't find it, you can switch and then, until you find the right team, then you can do the best work that you're looking for. So it's not financially very viable, but if let's say you are a person who's really, you don't care about money and you want to explore something new and interesting, then terahertz frequencies is one area to explore. Now, terahertz frequencies, there are no immediate companies to work for, because some of the engineers who have worked in this eventually come back to RF and microwave frequencies, because that's where industry works on and that's where you get paid. But there are some startups in terahertz frequencies, because this is a new field. So there are some startups. That's a risky path. Maybe you can take part in it, but it's a risky path. But in India, we don't have terahertz startups yet. Okay, it's a phenomenon in US and not in India. So generally, if you're planning for PhD, what I've spoken right now is PhD, and I'm just telling you where university is working and where research is working on, where industry is working on. Universities even now are working in all the areas, but if you see, America is generally more, what do you call? They are always proactive, and so they react. They actually guess what will be the future research and try to invest in their universities in those areas. So if you see, American hiring is mostly in this region. Terahertz is where all the top universities, Stanford, MIT, or Berkeley, that's where they're hiring. And the focus is in that area, the top schools. But there are schools where professors do work on these areas as well. Mixed signal research. Even in mixed signal, ADCs and PLLs, we are pushing them to their fundamental limits. It's very challenging to build an ADC with a very high bandwidth. It's extremely challenging to build an ADC with high bandwidth and high resolution. That's the challenge. Okay. And similarly, PLLs, it's very challenging to build PLLs with very high frequencies, which is in the order of, gigahertz, tens of gigahertz or hundreds of gigahertz, 100 in the sense, early hundreds of gigahertz, and build it with a high purity, meaning low noise. That's again a huge challenge. So some universities do work on this area, okay, but those universities are those places where the professors have started their research, 15 years ago. They have more or less done the initial stage of PLL and ADC research. Now they are continuing with that momentum. They are pushing for more and more, pushing for better and better performance from these blocks. But the new hires, the past 5-6 years or past 7-8 years, the new hires and the new trend where the university is more focused on is in terahertz range. This is the American university system. The problem with terahertz is that, as I said, if you're exceptionally good, if you feel that you don't have to worry about your competence, you're damn good, then it's not risky to choose this field, because uh, the options available are very few. If you want to come back to teaching, doing terahertz research, the teaching positions are not as much. But in US, it's very competitive, but not in India or some other places. It might not be that difficult to get a position, academic position. But if you are immediately planning to work in industry, your goal is to become an industry leader, then these two are the better areas to be focused on. And industry is doing phenomenal work in these areas itself right now. There are many good companies uh, in US and in India. So for example, India TI, there are some specific teams in TI who do brilliant work. There is a company called Aura Semiconductors. Um, okay. And then there is Silicon Labs, which I worked for. And Aura Semiconductor is it's a startup company, which was founded by engineers from Silicon Labs. So both have excellent work cultures. And then we have Max Linear, which is doing, again, brilliant work in the area of RF and mixed signal. Okay. Now, you have to keep one thing in mind. Most of these companies don't directly hire undergrads. Okay. So it either goes through some references, but they don't really generally prefer undergrads. TI is a big company. It has been there for nearly 40 years now. So that is one company which usually prefers undergrads. In India, I'm talking about India. United States, once you finish your master's, there are many companies which work at master's level. When you immediately they'll be ready to hire you after master's. There are many companies which work in different areas. Okay. Even in terahertz, you can also find some startups. But as I said, it's a risky path to take. It's a brilliant area to work on. It's a new area, so new problems. You will be the first one to work on it. Okay. It has been like many teams have worked on it for 5-6 years now. Some of the universities have also started experimenting with products, but it is still a very nascent stage. It will take another 10-15 years to mature, is what I'm guessing. Then those products will become common in industry. Okay. So that's about very briefly about different areas of research. So in case you have any questions, you can just type it in the chat window. I'll try to answer them while I'm recording itself. So can I talk about MS? MS then? Okay. So most of you, I'm assuming, are undergraduates. So MS is, see, there are few things you have to take a call. See, these things, I may give a suggestion now, but